So 6.1b is all about circular motion, and we're going to be talking about two things in this section: angular speed and linear speed. Now, that second bullet point, linear speed, I think we basically have a firm understanding of. It's the speed that we think of when we talk about how fast something is going. It's called linear speed because typically we talk about things going in a line. So, for example, I'm just making these numbers up. Say we had a racetrack and we marked the beginning as 0, I don't know, feet. And this here is, say, 50 feet. And I told you that this object started here and ended up here. And it took him, 10 seconds. And suppose I asked you, well, how fast is this object going? If he traveled 50, assuming constant velocity, he traveled 50 feet in 10 seconds. Of course, everyone is going to tell me that his speed, if he covered 50 feet in 10 seconds, is 5 feet per second, right? Because this is where he started, this is where he ended, so we can clearly see he covered 50 feet in 10 seconds. And that's sort of like the idea of linear speed, right? Linear speed may be thought of as the total distance traveled in a particular amount of time. This is the classic speed that we think of. It's always distance over time. Well, when it comes to circular motion, objects that travel in a circle, that sort of isn't helpful to us, or rather, we really can't talk about, start and finish, because let's suppose we had an object that started here, and this object traveled in a circle and ended up in the same point, right? In terms of displacement, he didn't go anywhere. He started in the same spot that he went. Well, it turns out that objects that travel in a circular motion actually do possess speeds, but they possess two types of speeds. One is the typical linear, but the other is angular speed. If you to track the amount of angles that an object covers in a particular amount of time, that's what we call angular speed. So angular speed may be thought of as the total angles quote traveled. Now I put the word traveled in quotes because you really don't traverse angles, you sort of like cover or rotate. So it's the total amount of angles traveled in a particular amount of time. So while linear speed is distance over time, we can sort of think of angular speed as, well, not surprisingly, angles over time. And I said it before that linear speed or circular motion has both speeds, linear and angular. How's that possible? Well, if you were to imagine this circle and you were to snip it, right, like sort of like cut the circle and sort of lay it down, wouldn't it sort of lay down in a straight line? Or another way to think about this is, imagine you had a wheel and you were to paint the wheel or cover the wheel in paint, and you rolled the wheel down. Well, wouldn't it sort of leave some sort of like marking if you were to take this wheel and roll it? wouldn't it sort of cover, it'll sort of leave a linear paint line. Now, that linear paint line came from the circumference. And that's sort of like the idea behind the relationship between linear speed and angular speed. You can easily convert one from the other if you think in terms of circumferences. So those are the big ideas, but I know some of you guys, you guys much prefer formulas. So here, let's go ahead and summarize everything in a nice box, nice table. Linear speed and angular speed. Okay. So suppose a point moves along a circle of radius r, and the ray from the center to the point traverses theta radians in time t. Then the angular speed is simply the amount of angles, the amount of radians, divided by the set of time. And then the linear speed is simply the arc length that it covered divided by the amount of time. Now remember this S symbol. This is what we talked about yesterday. Recall that S equals arc length. Right. And there was an idea or a formula to find it. Now, just as yesterday, okay, do you have to memorize these formulas? You could. They're not hard formulas. Angular speed, theta over t, linear speed, arc length over t. But I much prefer to solve problems using pure logic. So the types of problems you'll face in today's section will involve things going in a circle, right? You have a particle that moves in a circle. You are spinning a toy in a circle. A planet orbits in a circular pattern, those types of problems. And it's all you have to focus on is what's the amount of angles and what's the amount of time. Let's do an example here. Suppose a boy rotates a stone in a 3-foot-long sling at the rate of 15 revolutions every 10 seconds. Find the angular and linear velocities, or I should say speed, of the stone. So what's happening here is you have this stone here, well, do that, and it's attached to a sling, so basically a piece of rope. And this boy is spinning, wow, I can't draw, spinning that stone in a circle. And I want to find the angular speed and the linear speed. Now, we do have formulas for it, right? Here are the formulas. But let's tackle this logically, because I think if you understand the logic, then the formulas will naturally come from it. Before we begin, I do want to provide a little hint or a note. The word revolution means one full circle. Okay. So let's tackle this logically. What do we know? According to the problem, right, we have 15 full circles. Right? That's what 15 revolutions says. 15 revolutions, you have 15 full circles. What else do they tell? So what? What do we know? Well, we know, and every full circle is 2 pi radians. Therefore, the stone covers, if I want to figure out the total amount of angles that the stone covers, if he covers 15 full circles and every full circle is 2 pi radians, I hope that's very obvious. That's just 15 times 2 pi, which is 30 pi radians. Well, what else do we know? The stone covered this 30 pi radians in 10 seconds. Well, angular speed. Angular speed is angles over time. So how many angles do we have? 30 pi radians. What was the time that it take? 10 seconds. Therefore, the angular speed, the symbol that we use for angular speed is this omega symbol. It looks like a W. Is the amount of angles, 30 pi radians, over the time, 10 seconds, which is 3 pi radians per second. Easy peasy, right? So I hope, even though, yes, there are formulas for these, we did this problem from start to finish without referring to any formulas, using pure logic. Angular speed, just find the total amount of angles divided by the total amount of times. Now, if I want to convert that to linear speed, so that's the angular speed. That's half of the problem. The problem on both angular and linear. We just need to figure out what is the total distance traveled. Now, remember, we're talking about circular motion. So distance traveled in circular motion, you want to think of circumference. Well, again, the problem told me 15 full circles, right? It says the rock went through 15 full revolutions. And one full circle travels the circumference, 2 pi, and what was the circumference in this case? The circumference was 3 feet long, right? This is a 3-foot radius. So we know that in one full circle, it covers 6 pi feet. So the stone covers 15 full circles, and every single full circle is 6 pi feet, or in other words, 15 times 6, which is 90 pi feet. Well, according to the problem, the stone covers this in 10 seconds. Therefore, linear speed, the symbol that we use is v, is the straight up distance over time. His distance, 90, oops, I wrote 30, 90 pi feet over 10 seconds, which is what, 9 pi feet per second. So there we go. If you spin a rock with radius of 3 feet at a speed of 15 revs per second, or per 10 seconds, you're actually going 9 pi feet per second linearly, or 3 pi radians per second angularly. So when it comes to these problems, you got to think. Angular speed, total angles over total time. Linear speed, total distance over time. So that's about it. There are formulas to memorize, angular speed, linear speed here. But honestly, with these problems, it's just using logic. So for the rest of the video, if you're all good and set, feel free to go on and do the practice. But for the rest of the video, I'm just going to go ahead and just do some more examples, right? If you're all good, you can end the video here. If not, just listen up to more examples. Suppose we had a 26 inch diameter wheel, if I can spell, that rotates 125 revolutions per minute. Find the speed in miles per hour at which the wheel spins. Now, in this case, I wrote this example here just to show you that they may not be explicit in the instructions. The instructions just says find speed, but we're talking about two types of speeds here, angular or linear. And you might go, if this was a quiz or test, oh no, what are they talking about? I don't know. We'll use the question as a hint. It says miles per hour. We only have two types of speeds, linear and angular. Angular is angles over time. Linear is distance over time, and we should know that miles per hour is a distance over time. So although it doesn't say it, based upon the instructions, we need to find linear speed. Well, to find linear speed, we need distance over time. So what information do they give us in terms of circles? Well, they tell us it rotates 125 revs per minute. Okay, so we have 125 full circles at 2 pi times r. Now, in this case, the diameter is 26 inches, so the radius is actually 13 inches. So we know that this wheel goes 125 full circles at 2 pi times 13 per full circle. Therefore, total distance is 125 times 26 pi inches, right? So I'd take out a calculator. 125, where's my calculator? Here we go. 125 times 26 is 3250 pi inches. Well, what about time? I need speed, right? Well, it says per minute here, so I know total time is 1 minute. So his speed is distance over time, which is 3250 pi inches over 1 minute. There we go. Technically, that is the answer, but the question says miles per hour, so all we got to do is a little bit of dimensional analysis to cancel out the units to get in the proper units. So this should be a quick review. Let's go ahead and let's convert the inches into miles. So I know that there are 12 inches into 1 foot, and there are 50 to 80 feet in 1 mile, right? So that will take care of the miles. Now I need to convert inches into hours, and we should know that for every 60 minutes is 1 hour. So that takes care of the minutes. So then all you got to do is just take a calculator and see what that approximates to. So that's 3250 times pi times 60 all over 12 times 5280. So that's approximately 9.6, so let's call it 7 miles per hour. Notice, did I use any formulas to solve this problem? No. I mean, we could have, but we did pure logic. Now, sometimes the problems may go backwards. We've been using revolutions per time to solve problems, but here I might ask you to find the revolutions, and all you have to remember is 1 revolution is 1 full circle. So, for example, a truck with 48-inch diameter wheel is traveling 50 miles per hour. How many revolutions per minute do the wheels make? So again, in the previous two examples, they gave us the revolutions per time and asked us to find the speed. This example is just going backwards. It's giving us the speed, and it's asking us to find the RPMs. Since they gave us the linear speed, naturally we want to think of circumference, so we want to find the total distance traveled and how much distance is covered in one full circle. So again, I guess I'll write this down. It's so important. Since the info given relates to linear speed, the 50 miles per hour, we will think in terms of circumference, right? So, in one full circle, the wheel covers, what's the formula for circumference? 2 pi times the radius. And again, they gave us diameter, so the radius is 24 inches. So I know one full circle is 48 pi inches. Now I know that the speed of the wheels is 50 miles per hour. All we have to do is, go backwards, do dimensional analysis. Because what does this math say? This math tells us, therefore, one revolution equals 48 pi inches. That gives us a dimensional analysis conversion factor. So let's go ahead and answer this question. They told us 50 miles per 1 hour. We want revolutions per minute. So let's do the easy part first. Let's go ahead and change the hours into minutes. Well, we do know that 1 hour is 60 minutes. So that takes care of, that takes care of the hours. Now all I need to do is change the miles into revolutions. Well, how do I do that? Well, notice here, we're relating revolutions to inches. So I need to first change the miles into inches, and then I can go ahead and change the inches into revolutions. So let's go ahead and change the miles into inches. Well, we know that 1 mile is 5280 feet, and 1 foot is 12 inches, and it looks like I might need to move this guy here. There we go. And then as our previous work said, 48 pi inches equals 1 revolution. And then that should take care of our dimensions. So miles are taken care of, feet are taken care of, inches are taken care of. So all that's left with is revolutions per minute, which is exactly what the problem wants. And then you just go ahead and do math. Use your calculator. So you have 50 times 5280 times 12 all over 60 times 48 pi. So that is approximately 350 revolutions per minute. When you're going 50 miles an hour with 24-inch radius wheels, that wheel is spinning about 350 times per minute. So again, we started off the lesson with formulas, but as you can see, these 3 examples, we did it pure logic, no formulas necessary. And that's what I want you guys to practice, the logic. Good luck.